Welcome to the Mipar tutorial on optimizing steps. In this tutorial, we will review how to use the optimization function in the image processor to more objectively arrive at the desired processing parameters. And we'll use two examples for this tutorial. We have one of our same gamma prime images, which was shown in the creating a recipe tutorial, and I mentioned in that tutorial that we would be revisiting optimizing parameters, most importantly in a adaptive threshold step where the proper window size and threshold value was a bit ambiguous and required some subjectivity. So we'll take a look at this image, and we will also take a look at this image here, which is a composite between some binder and gravel particles. It's asphalt. It's the optical image of asphalt, and we're going to optimize one particular adaptive threshold step to determine the parameters for finding these, or part of the parameters for finding the smaller particulates. So to begin, let's open up the gamma prime image and load in the recipe that we made for this particular image. This is the same recipe that you have in your examples folder. Okay. Now what I will demo is, again, how to objectively determine the parameters for finding the larger precipitates, or the most important step, optimizing it, which is this adaptive threshold here. You see, as we go in and we choose our adaptive threshold parameters, window size and percentage, we can play with the percentage and we can play with the window size. And we know it's going to be somewhere in this range. It's probably not going to be all the way out here. It's probably not going to be all the way down here. But it's going to be somewhere in here. So both, I would say, window size and percentage in this case are subjective. Now, you very well may be able to arrive at a combination of parameters that more accurately quantifies, say, area fraction of these particles when compared to some other validating technique. I don't know what else you would use to measure volume fraction, maybe X-ray diffraction, something else. I'm sure you could set the parameters to match those results if you knew them ahead of time. That's the big challenge with image processing. What this optimization function or tool lets you do is develop more objective, rules-based recipes that are free from user bias, so that even though all of your segmentations are not necessarily perfect, and that in and of itself is an ill-defined concept because you're only ever comparing a segmentation to the image rather than the actual microstructure, which is always an unknown, and the image is always a convolution of the microscope with the microstructure. But this technique can at least let you start developing, again, rules-based approaches so that whatever error you have, it's hopefully as systematic as it can be from image to image, so that any trends that you extract from your microstructure data are legitimate. So we'll cancel this manual editing, and I'll show you the methodology for optimizing these parameters. So with the step selected, if it's optimizable, the Optimize button is illuminated. Click it, and this gives you a little setup interface. So we're going to compare the segmentation. In this case, the prior image is what we'll start with, which is the original, so these two are the same. We'll leave all of these the same. This just will let you see the segmentations as they're done. We don't need to save each one, which would save every frame of the movie and a movie file. And we don't need to see the histograms of what has been selected white and black at each step along the way. We don't need to do that now. We will use a subregion for this example, and we'll use this mutual information metric as the similarity metric between segmented and original. And we'll be comparing the images of the segmentation and the original rather than any of these other two things. So we'll hit accept, and because we've said we'll use a sub area, that's what this message is asking us to do. So we'll make a box, just like with cropping. We'll double click on the edge of the box, and I'll pick an area somewhere in here, because again we're trying to optimize these parameters for the secondary precipitates. So I'll pick an area that's pretty rich in secondary precipitates, these larger ones. And now it's asking you for a range. So what range of each of those parameters do we want to explore? Let's say we go all the way from 30 of a window size to 100 in steps of 5, and we'll vary our threshold value from 90 to 110 in steps of 1. And we'll click OK, and that's what it's doing now. It's varying and segmenting the microstructure with this one step at each value in that 2-parameter range that we just defined. And on the bottom here you're seeing mutual information calculated between segmentation and comparison image, which in this case is the original image. So now what it's showing you is a surface of one parameter versus another parameter versus accuracy, quote unquote, mutual information. And what you sometimes see is that in this case, the peak parameters, the one that yielded the highest combination here, 194, is at the edge of our parameter space. So we can't be certain that that's truly optimal. And I could expand this range more and more. What you would see though is that the range, the optimum set is always going to be at the range. And this sometimes is an issue when you have this severe variation in intensity. So again, because what you're doing is comparing your segmentation to the image, not to the unknown microstructure, you have to take into account what the microscope has done to the image, and you may need to make some modifications to the comparison image that make the image better represent the microstructure that you know you're trying to find. Not sure if any of that made sense, but let me show you what often gives you optimized results that better agree with what your intuition tells you should be the optimum result. If let's say I hit accept, what would happen is that, of course, the rest of the steps get automatically redone. And I'll just show you, for the sake of proof, that if I kept all these the same, but now let me take the window size from 100 to 300, and I'll double this so that it runs quicker, and I'll set this at 50 so it runs quicker. And we're just going to see what happens. So, like I said, the larger the window size, the mutual information just keeps going up and up and up. And at a certain point, we know this really shouldn't happen. So it's a pretty telling sign when this kind of thing happens. What we have found is a reasonable approach is this. So what I'm going to do first is, above this step, I'm going to put a original image recall. And this then just lets us add on top of the recipe now, but then always get back to the original right before the adaptive threshold runs. Above the call image, original image, I'm going to put an FFT filter. And as was shown in the FFT filtering tutorial, a high-pass filter can discard some of the lower frequencies, the variations in contrast from feature to feature, and more accentuate the edges, which is where we really want the threshold to be, which is what we really want the threshold to be considering, are the particle edges more than the messy contrast inside of the features. So I'm going to take this now and accept it. Of course, everything gets re-executed. And now below the FFT filter step, I'm going to set this in memory as restore image 1. Now the call original image step gets performed. We start doing the adaptive threshold again. Now when I go to the adaptive threshold, I'm going to say edit the optimization parameters. And for a comparison now, instead of the original data, I'm going to use the restore image data, the FFT filtered version. Remember, I'm still performing the adaptive threshold on the original image. I'm just using the FFT filtered version to compare the segmentation to. So again, the adaptive threshold is being performed on the original image. It's just getting compared back to the FFT filter to determine the optimum parameters. And that historically has shown us to produce maximum or maxima in parameter space that seem much more practical. So everything will stay the same. This will all stay the same. Remember, originally our optimum set was up against the edge of the parameter space at a window size of 100. So no, this step is not completely free of subjectivity, in all honesty. There can be a need for the user to first manipulate the image so that it best represents the microstructure they're trying to segment. This isn't necessarily a magical technique that tells you the right answer, since the image and what it has done to the microstructure is always a prime consideration. But now we see a peak in our parameter space window at 35 and 99. So, because in the beginning we knew the parameter combination was likely somewhere in that range, this I would feel much more comfortable using as an objective parameter set after I injected a little bit of my own knowledge by pre-filtering the image so that this was the comparison. And there we have it. So now at the very end, our segmentation looks like this. Of all of the precipitates, we have just our larger ones here and the smaller ones here. Now if you save the recipe with these two asterisks shown, this step would be saved in an optimized state, so the next time you ran this recipe on an image, that loop that you saw would get re-executed during recipe loading, so this 35 and 99 could change to something else for a different image. Since you used a sub-area, it is going to consider that exact same sub-area for the next image, which might not be the best sub-area. So if you are to optimize a step with the intention of saving it into the recipe, you likely want to pick entire image, even though the optimization will take longer, so that the entire image of the next image is considered. But if you're just using this tool once to decide a set of parameters, and then you unoptimize it and save the recipe, now these parameters are fixed and will always be 35 and 99. So using the sub-area initially for the exploration is just fine. Okay, so we'll move on to the second image that will be a little bit less involved. We'll load the recipe that was used to find these particles in asphalt. I'll show here is fixing one parameter of an adaptive threshold. Since we have a great deal of confidence in the window size, we'll fix the window size and we'll let the threshold value vary. So this recipe has a couple of layers, one to find the larger ones, one to find the smaller ones. And it, of course, the smaller ones especially, depend a lot on this fine windowed adaptive threshold step. So when we're setting these parameters, if we go in and we kind of take a look at the length scale of our features, we stretch this across, these fine scale features are on the order of 20. So we're pretty confident that 20 is a reasonable choice. You're welcome, of course, to always optimize both, but sometimes it's more efficient to fix the window size, since that's usually less of a subjective choice, and then let the threshold value vary. So that's what we're going to do here. Window size of 20, we're going to say optimize it. The prior image in this case is the original, so that's what we want. Sub area again. In this case, I'll show you using another parameter, intra-class variance, and in this case we want to minimize the intra-class variance. The intra-class variance briefly looks at all of the pixels that are turned black and looks at the standard deviation of those grayscale pixels that have been turned black, and then it looks at the standard or the variance of the grayscale pixels that have been turned white. So now you can imagine two histograms, those pixels that were turned black, those pixels that were turned white. You have a variance for each of those histograms. You average those two histograms together, and you're trying to set the threshold value such that the average variance of both of those histograms is minimum. It's the Otsu method, if you've ever heard of that, for choosing an optimum global threshold value. Softwares that have an auto button, like Mipar, for a global threshold are using most likely that Otsu method. And it's easier with a global threshold because you can just use the histogram. You don't have to perform the segmentation at each value like we're doing here. Mipar's optimization engine is much more robust in that it can be executed as you're seeing on steps besides simple global thresholding. So we're going to use, just to show you another approach, intra-class variance as another metric. And we do intend to add even more metrics as options in the future. So we'll say accept to this. We'll pick this small window over here that has a lot of these finer precipitates. And now we'll say, again, keep the window size from 20 to 20. Doesn't really matter what the increment is since there isn't a change, so we'll leave all that the same. And again, I'll let the threshold go this time from 90 to 120. Okay, and it comes back and it says choosing 110 at this window size gives you the minimum intra-class variance. So that's what we're going to pick as the optimum set of parameters here. So there are many other steps that you can optimize. Anything that lights up the optimize button is optimizable. I like to sometimes at the very end of a recipe say when you're and I can give you an example of that here. These guys, if I knew that I roughly had the particles identified, but I don't want to be over or under segmented, even by a pixel, since that can affect your area fraction, you can put at the very end, say, an EDM dilation step of even 0 to begin with. And now I'll optimize this dilation step. I can use the entire image here. We'll compare it against the original. We'll go again with intra-class variance, and we'll say dilate me from 0 to 10 in steps of a half. So now it's going to grow my particles from 0 pixels to 10 pixels in dilation depth, and tell me now hopefully good, that no dilation was necessary to further minimize the intraclass variance. So we know we definitely don't need to dilate these. And then you can also add on, you'll probably guess, an erosion step. And optimize it in the same fashion. 0 to 10 steps of a half. So now we're shrinking the particles by 0 pixels to 10 pixels and getting this metric at each step along the way. And fingers crossed, we come back, we actually needed to shrink the particles by a pixel in order to maximize or to minimize that intraclass variance. So that's good to know. And now you can have more confidence that you're not over or under segmenting your features. And what does that knowledge, or what does that over or under segmentation get you? Well, with an erosion here of 1, if we measure the area fraction, we have 27% of the larger features, whereas if we went to this step and also measured area fraction, come back with 28.7. And what was it before? 28.7 versus, show this image, 27.1. So almost 2% area fraction difference just from that 1 pixel erosion. So that can be costly. And if you had a choice, you'd like to be able to know whether that pixel erosion was necessary or not. In this case, you have a quantitative reason for making that choice. So that is the tutorial on optimizing steps. There's plenty more you can do with it. We can put out additional application-specific tutorials if desired. Send me any questions. Thanks very much for your attention, and we'll see you again soon.